Friends, let us move on to the third module on the online course Risk and Reliability of Offshore Structures. In third module, we are going to focus on risk assessment and reliability applications. So, in the third module, we will talk about the first lecture today, where I will talk about the fatigue reliability, as we discussed in the earlier two modules. Uncertainties are inherently present in an offshore structural system. These uncertainties can arise from various sources. Primarily, they are from the external forces or loads acting on the system, and implicitly there are some uncertainties which can arise even from the material characteristics, method of analysis, method of modeling, etc. So, probability tools were the best methods to implement all these uncertainties to as far as possible. But however, when you talk about probabilistic modeling, we also discussed about the shortage or difficulties using random variables. So, then we moved on to what we call Boolean variables, where I can use stochastic modeling. Stochastic modeling also has variation in terms of time. The variation in terms of space is compromised by using a specific vector. So, then we have also said how to estimate the system reliability for elements in parallel, for elements in series, for elements in brittle and elements as ductile. We moved on to estimate of probability of failure by considering the probability of exceedance of a specific value when compared with the threshold limit of that specific value, which is a very useful method and approach used in fatigue reliability. So, in fatigue reliability, essentially people use what we call SN curves. One of the common ways of fatigue assessment is actually based on direct calculation of fatigue damage. Is to directly estimate the fatigue damage. On the other hand, one can also estimate the expected fatigue life. So, interestingly, as said by Marshall in 1976 and Mustafa in 1985, fatigue assessments are essentially successful when one is able to estimate what is called fatigue damage. Now, one has to classify what is meant by a damage and why it is classified as a fatigue induced damage. So, therefore, an indirect fatigue assessment can also be performed, can also be made by limiting the predicted stress range within the permissible stress range, by limiting the predicted stress range within the permissible stress range. We are not talking about a specific value of stress, we always talk about a range of stress values. So, the fatigue damage is stated in terms of the stress ranges. Which are essentially produced by the cyclic loads. So, reversal of stresses are responsible for fatigue damage in any structural system, to be very specific, structural member or a joint. We know that all our external loads which arise from the environment are essentially cyclic in nature. Okay. So, the environmental loads act on offshore structures are capable of producing or inducing cyclic loads on the offshore structures. They essentially arise from the sources of cyclic loads, essentially come from wave amplitudes, wave direction, wind direction, though the velocity may not cause a very significant variation in open sea state. Interestingly, such loads which are cyclic are also dynamic. Therefore, put together the structural response under these actions will also be dynamic. When we talk about fatigue induced stresses, in terms of stress range, one should also consider the stress concentration. Because these stress concentrations are capable of modifying the capacity of the joints under active stress range. SN relationship So, SN relationship essentially represents the number of cycles to failure at various stress ranges. So, in offshore structures, a 2 segment SN curve is commonly used. Which is used for design application. It shows that n is a s to the power minus m if n is less than or equal to n q. On the other hand, n can also be C s to the power inverse t inverse r if n less than n q. N complement can be said as n t by t r minus m q for t greater than t 0 and n complement is n for t less than 3 a and 3 b, where S in these equations denote the stress range, n denotes the number of cycles of failure, at this stress range Tr is called the reference thickness and n corresponds to the specimen with Tr. N dash of course denotes the reduced number of cycles to failure after accounting for shell or plate thickness. In this case T, plate thickness effect T. A denotes fatigue strength coefficient, M and R are fatigue strength exponents. These can be determined based on experiments. So, interestingly, for offshore structures, or can be used as m plus 2. The above set of equations represent a 2 segment straight line in log scale. So, equations 1 to 3a represents a 2 segment SN curve in log scale. Of course, this curve will have a discontinuity at n equals n q. Friends, please pay attention to the 2 segment SN curve shown for different stress ranges, which is shown on the screen now. One can see here S is plotted as a stress range in megapascal in the vertical scale or axis, and the cycles to failure n is plotted in the horizontal axis, varying from 10 to the power 4 to 10 power 8 cycles. The red line shows actually the 2 segment SN curve. One segment is this, other is this, whose slope is different. Therefore, the line is discontinuous at n equals n q. Now, traditional SN curves are also used in the design of offshore structures. If you have a case where for n exceeds or equals n q, this signifies what is called endurance limit. This implies that a member can endure for all stress ranges S less than equals S q, indicating no fatigue damage in this range. In early years, in the design of offshore structures, conservative approach was used by ignoring this endurance limit. Designers have used conservative approach by ignoring this endurance limit. The reason stated for this was to account for corrosion fatigue. Essentially, the conservative approach was supported by a statement accounting for corrosion fatigue. That was the reason why it was considered to be very conservative. (1987). Patin, Stanislav, 1999. Subsequently, with the accumulation of large amount of experimental data available, with the availability of large amount of experimental data, the conservative approach was overcome. Now the consensus is, what people use is to use the 2 segment SN curve. Let us look at different parameters recommended by ABS code for using this SN curve. I request you to pay attention to the table shown on the screen now. For class T offshore structures, parameters for SN curves are recommended by ABS code, American Bureau of Shipping, where A, C, R and M, NQ and SQ are available for different class of SN curves as designated by ABS. Interestingly, the recommendations made by ABS code indicates that for service in seawater, that is for using members in seawater with free corrosion, there is no change in the curve of the slope. There is no change in the, let us say, in the slope of the curve recommended by the code. As we discussed just now, SN data or the curves for SN data are derived from experiments. Now, these experiments has one unfortunate identity, that all thickness or all plate and shell thickness are not included in the test data. Some of them which are of practical interest are not included. So, that is a very unfortunate issue, but it is true. Some of the plates and shell thicknesses which are commonly used in offshore structural members do not have a segmental representation in the experimental verifications for preparing the SN data as recommended by various codes. As thickness correction or including thickness in the SN curve estimates will show a reduction in the stress range capacity or stress range acceptance of the SN curve. So, thickness also plays a very important parametric role in choosing an appropriate SN curve. Now, I have an SN data which does not accommodate all practical values of plate thickness what I am going to use in my structural system. Therefore, SN curves are traditionally determined by constant aptitude tests. determined by constant amplitude test. Of course, for large stress ratios, the ratio of minimum to maximum stress is about 0.5. What is the consequence of making a statement that SN curves traditionally use constant amplitude test procedures? This implies a major fact that the stress range considered in the data of experiments is in crack opening mode. Now, let us look into few factors which makes the SN curve conservative. One, relaxation of residual stress. Residual stresses are not introduced. Two, external stress being partly compressive. So, as a result of which cracks will have closure effects. So, what we call crack closure effects. These factors would make the actual crack growth lesser than that is estimated. So, the implications or the consequences could be 1, the actual crack growth is lesser than that implied by the stress range used in SN curve. Interestingly, while it is good to know that the approach is conservative, the bad news is they deal with constant amplitude. That is what you said here. Okay. So, traditional SN curves deal with constant amplitudes and they are conservative because of the above indicated factors. But in reality, environmental loads that act on offshore structures have variable amplitudes. Therefore, what is the solution for this? The SN data be used with thickness correction. for offshore structures. Now, the recommended reference thickness and exponent Q are given in the table of form for both plated and tubular joints. So, the recommended thickness and the exponent to be used in this equation are now shown in the table of form. An alternate way of thickness adjustment is to define the thickness which is adjusted for a stress range. So, one is to exactly use the recommended thickness as given by the table, which I will show you just now, but however alternatively one can also use or one can do thickness adjustment to define a thickness that can withstand the variable stress amplitude for a given stress range. So, SF can be S T by TR minus Q for T greater than T0. SF can be simply S for T less than or equal to T0. Let us call this equation number 5. So, we are looking for the thickness correction where TR is the reference thickness, and we are looking for the recommended values of this exponent Q, which one can see from the table as shown in the screen now. One can look at the parameters used in this equation 5, that is TR and Q, given by different codes as referred there on the top for different kinds of values of Q and TR for reference thickness varying from 16 millimeter to as high as 25 millimeters. So, this is what recommended for the design of offshore structures, which accounts for or which accounts or accommodates the variable amplitude values and of course thickness, which are not included in general in the experimental specifications. Alternatively, one can also look at the equation based on which you can define the thickness by thickness adjustment. Similarly, for the tubular joints, ladies and gentlemen, please look at the table shown on the screen now for varying values of Q and TR as recommended by different codes as indicated on the top. Again here the reference thickness for tubular joints varies from 16 millimeter to as high as 32 millimeters, as you can see in the table. Now friends, we are talking about estimating the fatigue damage for a member or for a joint, which is only one part of the failure of the structure. Now, but one is interested to know estimating of cumulative damage. So, commonly used hypothesis is linear damage hypothesis, which we will explain now. Palmgren-Minner's rule supplements for the constant amplitude for the problem associated with constant amplitude stress range which is one of the important issue, but not a serious concern when applied to offshore structures. This actually allows This actually allows a number of different amplitude cycles and then the fatigue damage is assessed based on this rule. Which is the Palmgren minus rule. Based on this, fatigue damage of a joint under n number of cycles of constant amplitude is considered for the design. The cycle ratio which is used in this case is simply n over n. Now, if you have a joint, if the joint is loaded with variable amplitude, then the loading cycles can be divided into groups of approximately equal stress ranges. You have to group the stress ranges and then you can use, for every group one can use a cycle. Let us say there are G such groups. With almost equal stress range. Then one can say SG be the stress range of the group, where G stands for the group, and Ng be the number of cycles in each group, so one can then find the fatigue damage is given by D of the group, the damage of the group is Ng by Ng, where Ng is given by A Sg to the power minus m. Equation number 8. Minus rule states that failure under variable amplitude will occur when the following condition is satisfied. That is, summation of G equals 1 to the total group capital G, dG becomes unity. This is what we call as failure spectrum. So, friends, in this lecture, which is the third module, lecture 1, we have started discussing about the fatigue reliability, where we are interested to know fatigue is a kind of failure in which the stress value or the stress range exceeds an accepted limit under the cyclic loads, where offshore structures are very common victims of these kind of cyclic loads, where the amplitudes can be a variable which is of a reversible in order. Even the directions of application, including wind and wave forces, can also form cyclic effects on the members. We said how to estimate using an SN curve. We also discussed about the factors based on which SN curves show a conservative estimate. Two main issues on the SN data based on which are constant amplitude experiments and thickness of a reference value, which are not common in offshore structures, cause a real worry of conservatism in SN data. This of course can be handled by making the plate thickness correction and the factor of the exponent power q as recommended by various codes, as we saw in this lecture. We will further discuss the details about the fatigue spectrum and application of this damage, cumulative damage models in offshore structures in the next lecture. Thank you very much.